Good.
We're good?
Yep.
All right. So we're going to talk about, first, we're going to talk about, why Bode plots, work. How, the theory behind the Bode plots. This is stuff that we've been jamming down your throats since Circuit Theory 1 and through the electronic sequence, where we've worked in the AC, the frequency domain. You learned about capacitors and Laplace. But I'm just going to back it all up and one time go through it mathematically rigorous. Try to go through it with theory, so that you to justify what it is we're doing with Bode plots. Then we'll do a Bode plot example or two. So the first thing is I keep talking about this Laplace variable. And it's S. And the Laplace variable, as you learn in differential equations, makes all that differential equation nonsense go away. It becomes algebra. So we really like the Laplace variable. And we think about the Laplace variable as having a real part and an imaginary part. And we use Greek letters, sigma for the real part, and that looks like a W, but that's omega for the complex part. And we think about the fundamental, the basis for all signals, e to the st, the basis for all signals. Here's a signal, a complex exponential, that has both the time domain and the frequency domain as part of it. And so you've learned through the Fourier transform and then the Laplace transform, right, that this signal, this basis that can represent any signal, including DC, right? If S is equal to 0, e to the 0 is 1, right, including DC. This is any signal you want it to be. E to the st, e to the sigma, times e to the j omega, e to the st, e to the sigma t, e to the j omega t. We have a real part, an exponential raised to a variable that's a function of time. If sigma is less than 0, this is going to decay. If sigma is greater than 0, this is going to explode. We always learned that if S is in the left half plane, you're talking about a stable signal. It's going to decay to 0 over time. If S is in the right half plane, meaning sigma is greater than 0, you're going to have a signal that's not stable. It's going to plus or minus infinity. E to the j omega t is our fundamental sinusoid, our complex exponential. It's the cosine of omega t plus j sine omega t. Okay? This piece over here doesn't decay. It moves around the unit circle. Cosine squared plus sine squared equals 1. This is the unit circle. This is going around. How fast it goes around the unit circle, how many radians per second is omega. That's the frequency. Time domain's in there as well. You got t. You get the time. This is the sinusoid. This is the decay or growth or constant portion of that. Everybody understand Laplace variable? Any questions there? Okay, so where did we use it? Where did we use the Laplace transform? One place where we used the Laplace transform to make the differential equations go away was in the situation when we wanted to describe a system. Now, in control theory, we describe our plants with G's generally. Right? We got G of t representing the impulse response of the plant. You hit the plant with an impulse, and the output is going to be the impulse response. We did the Laplace transform. Oops, I went to H. That's my signals and systems. So the input U of t, the impulse response G of t, we get some arbitrary output through the process of convolution Y of t. All this is happening in the time domain. In the frequency domain, we're looking at the transfer functions. The Laplace transform of the input, U of t is U of s. The Laplace transform of the impulse response is the transfer function. Multiply, convolution in the time domain, multiplication in the frequency domain, multiply U of s times G of s, and you get the output in the frequency domain. So we, in control theory, and a lot of people in systems theory as well, prefer to work in the frequency domain, work under the Laplace transform, because it's going to be easier math. It's going to be algebra as opposed to all that calculus stuff. Beat the heck out of those differential equations. Questions? That's the transfer function. The frequency response of our system, G of s. The Laplace transform of the impulse response is the transfer function. We just called it G of s. We noted it was the ratio of Y of s to U of s. Your handout says differently because I used the signals and systems F there. It's just the ratio of output to input. The ratio of output to input can be expressed as the ratio of two polynomials. Algebraically, you'd be tempted to say y equals p and u equals q. That's not the case. This is a gain. The gain as a function of frequency, where the frequency variable is s, or maybe you'll make sigma equal to 0, and the frequency variable will be omega. This is the gain of the system as a function of frequency. That's what we're after. All we're saying is we can express that as the ratio of two polynomials, p and q. P and q letters can be arbitrary at this point, but you see them in a lot of signals textbooks. You all in this room recognize the signal textbook is Laplace. I'm not Laplace. I'm not receiving anything for plugging his book. Great book. Great book. Okay. So far, so good? So now let's talk about polynomials. We've gone from S, we've gone to transfer functions. Now we want to talk about polynomials. P of S. Pn s to the n. Plus bn minus 1 s to the n minus 1. Plus dot 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 plus b1s plus b0. I'm sorry. For p, I would like to use m as the variable. P is an nth, the letter m. And this one, oh, I did this one, thank you, sir. P is an n-order polynomial in general. We usually use the n for the denominator. Q is going to be an nth order. S to the n plus a to the n minus 1, s to the n minus 1, plus dot 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 plus a1s plus a0. M order divided by n order. M is usually less than n. Mathematically, m can be equal to n. M can never be greater than n. That's a system that predicts the future. We wish we had one of those. Come on in. Questions? Keep going. Poles and zeros. So we're talking about a transfer function that's the ratio of this polynomial to that polynomial. And it's a game. A zero is the solution to the equation p of s equals 0. Anywhere we can find a value for s that makes this polynomial equal to 0, we found a frequency where this system will have no output because p is 0. Anywhere we find a solution to q equal to 0, we found a frequency where this system is not stable. The output is infinity. We're dividing by 0. We call these solutions the zeros. We call these solutions the poles. There will be as many solutions as there are order. So there are m solutions. There are m zeros. There are n poles. These poles and zeros, because now we're taking the problem to just a problem of solving a polynomial. Okay? We can solve it for zeros just as easily as we can solve it for poles. Forget where I was going with that. M solutions here, n solutions there, poles and zeros. We've taken the problem from one of gain to one of solving. Oh, the types of solutions, I do recall now. The solutions come in kind of two flavors. You can have a first order solution, a real solution. S1 equals some real number, positive or negative. Or you could get a pair of complex conjugate solutions. You could get S1 comma 2 equals a real part plus or minus a j times an imaginary part. So we're trying to take this complicated thing, what is the frequency response of a system, and break it down into more manageable chunks that we can think about. And now we're going to be thinking about first and second order systems. Make sense? Questions? Okay. I guess before I go to first and second order systems, I want to go to this fact. You want to know the frequency response. So we're starting with a Bode plot here, where we're going to be looking at something as a function of frequency. We're going to set s equal to j omega. We're going to be thinking about sinusoids. How does this system respond to a sinusoid of varying frequency? We're going to make sigma equal to 0. And so we're going to have p that ends up being a function of omega and q that ends up being a function of omega. And since this was a higher ordered polynomial and omega is, j omega, it's complex, well, what we have is this is complex. And that's why I drew two pictures over there. We want to find the magnitude of g, and we'll show my chalk, and we want to find the angle of g. Magnitude and phase. We're going to have a gain that is complex, hard to plot in 2 dimensions without 2 plots. And rather than go polar, look at the real and imaginary part. Rather than go rectangular, we're going to go polar notation. We use magnitude and phase. And so the magnitude of g of omega is going to be equal to the magnitude of p of omega divided by the magnitude of q of omega. And the angle of g of omega is going to be the angle of p of omega minus the angle of q of omega. Angles subtract, angles add, magnitudes divide. Now, doing this in arbitrary order, you saw just writing those two formulas was complicated, right? So let's go with the factored view. The magnitude of g of omega is equal to some gain, k0, times the magnitude of p1 of omega times the magnitude of p2 of omega, dot, 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 magnitude of pm of omega. The product of each of the factors. If we can find the magnitude of each of the factors, we just multiply them together, and we can find the magnitude of the numerator and the magnitude of the denominator. Qn of omega. Similarly, we can subtract, add and subtract all the angles. The angle of g of omega is equal to, well, the angle of a real number is 0. So I can just ignore that term. And I'll get the angle of P1. I'll add to it the angle of P2, all the way out to the angle of PM. Subtract from it the angle Q1, the angle of Q2, minus dot, 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 minus the angle of Qn. Now, I don't know about you, but I find addition easier than multiplication. If I want to add things graphically, adding, this line plus this line, I can do that graphically. I can do that almost in my head. I can add things very easily. Multiplying those two is much more difficult. So I'm okay with this, and this is still looking like it's hard. And so the thing that we're going to do, the thing that Bode plots do, is they work in a log-log domain. We're going to take the logarithm of this. So the log of the magnitude of g of omega is equal to the log of k0 plus the log of P1 of omega plus dot, 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 all the way out to the log of Pm of omega minus the log of Q1 of omega minus the log Q2 of omega minus dot, 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 all the way out to the log of Qn of omega. Okay? If we do that, we will have terms that we can just add and subtract from one another to create a frequency response. If we do that, forgot where I was going with that one, too. If we do that, we will get terms that we can add and subtract. There are But if we've gone with the factored view, which we want to do here, we're going to have terms that are first order or second order. Only two kind of things we've got to know about, a first order term and a second order term. And then we can draw the plots from there. Okay? Questions? You guys are quiet. Is that because the camera's on? Okay, let's take it to the next level. I know there was another point there. It'll come out. Don't recall what it was. Okay, so accidentally erased my angle of G over here. Decibels. Christopher, you remember decibels?
A little bit.
Well, if you got a number, x, and it's in some linear form, you take the log of it, you multiply by 20, you're going to find out what x is in decibels. Okay? Decibels is a logarithmic scale. And every time the ratio that you want to convert to dB changes by a factor of 10, you pick up or lose 20 decibels. So what's the log of 100? All at once? 2. The log of 1,000? 3. The log of 0.1? -1. Every time I move by a factor of 10, the logarithm, log base 10, changes by an integer 1, and we either pick up or we lose 20 decibels. So we're going to do the magnitude here in decibels, because that gives us the logarithm that turns multiplication into addition. Okay, decibels. Covered. Now, I said that this is going to end up being a log-log plot. And the nice thing about that is, if this is 1, 10, 100, so I'm going up by a decade, this is going to be 20, 40, 60, I'll be going up 20 dB, down 20 dB for every decade in a first order system. Now, I'm going to explain that in a second. But the bottom line is, I want to use a log scale and a log scale in order to get nice straight lines. And so if I've got a log scale for frequency, where do I plot 0? Where do I plot DC? Seeing the head shape, we can't. The log of 0 is minus infinity, it's way over here someplace. So we have a special case with our first order systems. First order systems are systems that look like this. Special case. K0 s to the nth power. N is a positive or negative integer. This is a case of a first order, and the solution, setting this equal to 0, the solution is at the origin. S to the n equals 0. If this were s squared, there'd be 2 solutions at the origin. If this was s to the minus 1, there's 1 solution at the origin. So this is an example of a first order system. I've given it gain. And here's another example of a first order system. S divided by omega p plus 1 raised to the plus or minus first power. Okay? So if it's raised to the minus 1 power, s is in the denominator, we're talking about a pole. If it's raised to the positive first power, s is in the numerator, we're talking about a 0. It's first order. The solution to this one, just to keep things clear, let me move this over. S divided by omega p plus 1 raised to the plus or minus 1. And the solution is going to be S equals 1 over omega p, and it's in the left half plane. I'm sorry, S equals omega p, negative omega p. It's in the left half plane if omega p is positive. Both of these are first order. Both of these have real solutions. On the S plane, one has a solution here, the other one has a solution elsewhere on the real axes. The only difference between this first order and this first order is that the top one, when the solution is at the origin, it can't be plotted here. You can't plot the frequency of the solution. You can plot what that system is doing at any other frequency, but you can't plot at s equals 0 or omega equals 0. Does that make sense? Okay, so we got the first order, and then we're going to need the second order. Second order polynomial. I'll come back to my imaginary plane in a second. The second order polynomial, s divided by omega n squared plus 2 zeta. The Greek letter zeta is generally used there, divided by omega n times s plus 1. This, too many parentheses on this side. This whole polynomial gets raised to the plus 1 or the negative. It's a second order polynomial all by itself. Either it's in the numerator or it's in the denominator. If it's in the numerator, we're talking about a 0. If it's in the denominator, we're talking about a pole. So I'm trying to sort of bring down the scare factor. We've only got two things we've got to talk about. We've got to talk about first order, we've got to talk about second order. We've got these real complicated transfer functions with lots of zeros and poles, and all we really need to understand are first order and second order things. Whether they're in the numerator or the denominator, it is going to matter. And this can be, in the numerator, denominator, positive or negative as well. But there's really only two things that we're dealing with. I said I'd come back to the S-plane. We should do that. The interesting thing about this polynomial, the way it's written, where you have a pair of complex conjugate roots, a couple of interesting things about it. The real part is always determined by this term right here. Hello, hello. The distance from the origin, the magnitude of these roots is omega n. This term here. You may see an example polynomial, s squared plus 2s plus 100. You're looking at a second order system as an example, and you're saying to yourself, omega n is 10. It's the square root of this number. You're taking this number, you're dividing it out in order to get the gain down to 1. There is that number squared. The square root of this number is going to be your natural frequency. Okay? Play with that a little while. Questions so far? So, if we're talking about K0s raised to the nth power, we're talking about K0 times j omega raised to the nth power, because for the transfer function we're going to set sigma equal to 0. If we want to convert this into decimals, 20 times the log of this, the logarithm is going to turn multiplication into addition. We're going to have 20 log of K0 plus n times, 20 log plus n times 20 log of omega. When we go to plot that on a Bode plot, if we think about frequency logarithmically, say this is 0.1 radian per second, 1 radian per second, 10, 100, 1,000. At 1 radian per second, where the log of 1 is 0, we're only going to have gain. Whatever we got is right there. It's 20 log K0. It's the gain of the system converted to decibels. Now, if we had a single 0 at the origin in the numerator, that means n equals positive 1, we're going to go up 20 decibels for every decade. This line has a slope of positive 20 dB per decade. If we only had one of them, but it happened to be in the denominator, and would be minus 1, we'd be going down 20 dB per decade. If we had 2 of them in the denominator, if we had something over s squared, we'd be going down at 40 dB per decade. See that? The only thing that's changing is the slope of the line. All of them go through the gain point at 1 radian per second. What's the angle? We're talking about the angle of K0 times j omega to the nth power. Well, what if n was positive 1? We're talking about something that has, this is real, this is imaginary, as omega is going up, we're heading up that axis. The angle is plus 90 degrees. What if the n was positive 2? J times j is minus 1. We're going this way. We have a real number, but it's going in the opposite direction. It's positive 180 degrees. If n was positive 3, we'd be going 1, 2, 3. We're going to pick up 90 degrees of phase shift for every n. So in the case where n was positive 1, we're down here at plus 90 degrees, positive 90 degrees, and it's a constant for all frequency. If n was positive 2, it would be 180. If n was minus 2, it would be minus 180. The phase of this kind of a root, a real root at the origin, the phase is n times 90 degrees, whatever n is. You now know everything you need to know about first order roots, whether they be poles or zeros, I'm sorry, zeros or poles, at the origin. Any questions about that? Hearing none, try to reuse this carefully drawn Bode plot, set of axes, and talk about what happens when the real solution, the real root of the polynomial, is not at the origin. In that case, we're dealing with 20 times the logarithm of s divided by omega p plus 1 to the plus or minus 1 and we got to think about it in two different regimes, two different regions. When s is really small, when the frequency is really low, what's the solution to this equation? Anybody see it? When s is really small, what's that? So you're taking the log of 1, you're getting 0. Sorry. I had a mistake here, so I owe you guys a new handout. Throw me for a second there. For really low frequencies, 0 decibels, which is a gain of 1. For really high frequencies, when s is much, much higher than omega p, you can ignore this term, and you're going to get 20 log frequency divided by 20 log omega p. So, depending on whether this is plus or minus 1, you're going to get plus or minus 20 times the log of omega minus 20 times the log of omega p. And so the way this would look on a Bode plot is we would pick a line and we would call this 0 decibels, and every unit below would be dropping 20 dB, minus 20, minus 40, and the above would be growing. And we would be heading out this line until we got to omega p, some parameter, some pole frequency. And when we get to that frequency, wherever it might be, put it here arbitrarily, we're going to break either in this direction or in this direction. The slope's going to be plus 20 dB per decade, or it's going to be minus 20 dB per decade. And which it is depends on whether this is plus or minus. And I guess I should put parentheses around there to make the plus or minus clear. Okay, again, we're thinking about s divided by omega p plus 1 to the plus or minus 1, and we're thinking about the angle. What's the angle of this at really low frequencies? Angle 0. What's the angle of this at really high frequencies? Well, it's going to be, this is complex number. Really high frequencies, this becomes negligible. It's going to be either plus 90 or minus 90. And so we'll start at 0 degrees. And we're going to end at either plus 90 degrees or minus 90 degrees, somewhere out here at really high frequencies. We're going to be starting down here at 0. And when we get to omega p, we're going to have to be thinking about breaking either to the plus 90 or the minus 90. Now this is where you're thinking maybe 45 degrees. Right when s is equal to omega p, I have a situation where I have this way, where we have a real number and an imaginary number that are equal. Okay? So right at omega p, we're going to have either positive or negative 45 degrees of phase shift. Just as a rule of thumb, a reasonable way to plot this, we're just sketching, we'll use MATLAB or Scilab when we want to do anything with detail. We're going to have to go an order of magnitude, we'll go in an order of magnitude, out an order of magnitude in frequency. So 1 decade in, 1 decade out, we'll plot the transition from low to high frequency phase. I guess we're running short on time. And so I'm just going to speed quickly and hand wave through a second order. Second order is just like the first order, only there's going to be twice as many poles. And so the exact same thing is going to happen. We're going to have at 0 dB all the way up until the natural frequency. And at the natural frequency, we're going to break, but the rate of change is going to be twice. Because we're going to have an s squared term. And so in the log that'll come out in front, we're going to have 40 decibels per decade. For a second order pair of complex conjugates, we'll have 40 dB per decade in slope change, and we're going to have 180 degrees positive or negative in terms of phase change. So there you have it. Much longer than we thought it was going to be. All you need to know how to do is plot magnitude and phase for first and second order polynomials. Any questions? We can kill the camera, Chris, and we can start class.